Hello, everyone. Thank you for being here today. And thanks to the Society of Exploration Geophysicists for inviting me to present to you today as part of their applied science education program. So I'm really excited to be here today to talk to you about one of my favorite things, which is moon rocks. In particular, the rocks that were brought back by astronauts during the Apollo missions back in the 60s and the 70s. These rocks were basically the prize at the end of many decades, maybe even centuries worth of studying the moon. And I hope that by the end of this talk that you'll see how important these samples were in not only changing how we think about our moon, but also how we think about our whole solar system and how we fit in to the area around us within the solar system. So before I get going, I just wanted to tell you a little bit about me. So I'm Dr. Carolyn Crow. I'm an assistant professor at the University of Colorado Boulder, and I'm in the geological sciences department. And you say, well, why are you in the geosciences department when you study the moon? But actually everyone who studies meteorites and moon rocks or any rocks that aren't from Earth are all also geologists, because we have to understand rocks first and foremost. So. But my background, I did my undergraduate actually in astronomy, and then my research mentor handed me an iron meteorite and said, this is a piece of the core of a planet that no longer exists. And that was super cool to me, and I was hooked. So I changed directions, and I went and studied geology and geochemistry for my, my master's and my PhD at the University of Colorado. University of California in Los Angeles. And that's where I really got into studying moon rocks. You can see me over here on the left. This is in the Johnson Space Center Lunar Laboratory. This is one of the NASA centers where they house all of these samples. And I'm also really interested in meteorite impact craters, mainly for understanding these samples that we get from the moon. So I consider myself what we call a cosmochemist, which is basically an astronomer and a geologist put together in one. So that's what I do. Okay, so let's get going and start talking about the moon. So I like starting all of my talks, no matter what it is, for outreach, for talks for my students in my class, or for more scientific talks that I give, I like to start out with this view, looking at, over here on the left is the near side of the moon. This is what we're used to seeing, right? When we look up in the sky, these dark areas are what make the eyes of the man on the moon. But what we don't think about very often is what the other side of the moon looks like. So the moon always faces the same side to us. So we always see this view on the left. But on the right, this is what our far side of the moon looks like, okay? These are from images of spacecraft that we have orbiting the moon. And it's very different, right? It's very different. You can see right away that the moon is a very complex place, okay? We can see that there's, on the right over here, there's many, many, many craters, right? It's much lighter. There's whites and light grays. And then over here on the left, we do have craters. There's some really bright ones like Tycho and Copernicus, but we also have a bunch of this really dark material, okay? Which is very interesting over itself. So we, as lunar scientists, we talk about this lighter material. It's also very high. The mountains are very high on this side. So we call this the highlands, okay? And then we have these dark areas, and these are what are made out of what we call basalt. So if you think about Hawaii and all of the volcanoes that are forming there, all the lava that comes out once it cools and it gets very dark, this is very similar. Not explosive volcanoes, but they're called what we call flood basalt. So it's lava that's come out over the surface and filled in these craters, okay? So this is what we're trying to understand. We're trying to understand the moon as its own object. How do these craters form? How old is the moon? All of these kinds of questions. And people have been wondering about this for a very long time, okay? So I'm gonna take you through a little wander through history of lunar science, right? And we're gonna start all the way back with Galileo, okay? Back in 1609. So Galileo was the first scientist to really study the moon in more detail, okay? So he Here's a picture or a drawing of him looking through his telescope, and he was the first person to draw these very detailed images of the moon, right? You can start seeing the craters that are highlighted here along where there's the transition between the light and dark side, okay? And, the observations that he made might seem really basic to us today, but they were very revolutionary for his time, right? So he looked up at the moon, he said, okay, so the moon has mountains and it has valleys, but there's no clouds and there's no water on the surface, okay? So it's very dry. So Galileo was our first person to study. So as we continue through the 1600s, there were many other scientists that started drawing more and more detailed maps as your telescopes get bigger, right? Johannes Hevelius was the first person to do like a really detailed map of the moon in 1647, where you can start to see some features that might look familiar. Remember, this is that crater Copernicus and the Tycho. Those are the really bright ones. You can actually see Tycho with your naked eye when you look out at the moon, okay? Continuing on, a couple of years later, Grimaldi made a map, and he actually named everything on the surface of the moon. And this is how we still name things on the moon. So he basically set up the system in 1651, and that's how we still name things. So if there's a crater on the moon and you want to give it a name, we follow his system, which is pretty cool. So as we keep on going through the 1600s, right, the maps get more and more detailed. You can see Hevelius makes another one in 1696. Giovanni Cassini's got one in 1679. They're getting more and more and more detailed, okay? Also, the 1600s was a big lunar science time. And also during this time, we have Robert Hooke, who decides to do some experiments to understand where the craters on the moon come from. So as we get more and more detailed maps, we can see there's more and more craters at smaller and smaller sizes. And so one of the questions that kept coming up is, how are all of these craters being formed? If we look at the surface of Earth, we don't have craters all over the place, okay? And there's two ways that we can form craters, okay? We can either form it by impacts, meteorite impacts, or we can form it by volcanoes. Okay, these are calderas. These are basically collapsed tops of volcanoes. They create craters. Okay? So Robert Hooke decided to do some experiments to try and see if he could produce craters that look like the ones that we see on the moon. So what he did to simulate the impact craters, right? He dropped some balls into wet clay. These are experiments that you can actually do in your classroom or at home. You can try out different impactors of different sizes and produce all these different cool craters. And then he also boiled alabaster to try and produce similar craters. And what he saw was that basically the shape of the craters that were produced, these impact ones looked the closest to what we see on the moon. But at that point in time, they did not know of any source of objects that could be hitting the moon. We don't have a bunch of craters here on Earth. So they kind of ruled it out and said, well, it must just be volcanoes and just something that we can't recreate in the laboratory. Okay? So that's where we start in the 1600s. Okay? And then basically nothing happens in lunar science for about 200 years. They did all these maps, all these experiments, but then we kind of reached a limit where we couldn't do anything else, right? Telescopes weren't, advancing to the point of getting as much more information, okay? So the next step kind of in understanding lunar science comes from advancements in understanding impact craters, okay? So in the early 1900s, Daniel Barringer and Gene Shoemaker, this is a picture of Gene Shoemaker over here on the left. So they were the first ones to suggest that some of the craters on Earth were created by impacts, right? In particular, this crater here, here's a picture of me at this crater that you might be familiar with. So the name of this crater that you might be familiar with is the Barringer Meteor Crater in Arizona. Okay, this was originally called Coon Butte, but Gene and Daniel were the first ones to suggest that this was produced by a meteorite impact. And in fact, now we know that it was produced by a meteorite impact about 50,000 years ago. Okay. So they started a whole field of impact research. And what aided them as well was the advent of digital aerial photography, right? So around this time as well, we can get in a plane, we can take our camera, we can fly around, and we can take pictures of Earth's surface. And what they found was that there's a lot more craters that look like impact craters than we thought before, right? So here's some pictures, examples. So this one here in the middle on the bottom is Manicouagan. And then over here on the right is Clear Lakes. These are both in Canada. Okay, so we saw that basically these are more abundant than we thought. So that's interesting. That means that actually Earth is getting hit by things a lot more often than we think. And it has been hit by things relatively recently. So we no longer have this issue or this problem that Robert Hooke was having of not having a source of objects hitting the moon, because anything that hits the moon, there's going to be stuff that hits Earth as well, right? Or much bigger. So we also took those photographs, right? The ability to take photographs, and we pointed it upwards, right? We also had advancements in how we can look at the moon, right? So also in the mid 1990s, right, we get what we call the Lunar Atlas. So this is basically digital or photographic plates, images of surfaces of the moon where we can see different craters in much higher detail, right? So this is like the advanced maps, way beyond, right, what we could see in the 1600s. So we start seeing even more and more craters, and it's more and more complex, okay? It's very interesting. So what happens right after this, right, after this production of the Lunar Atlas, or around the same time, is we have this transition from just being able to sit here on Earth and take photos to actually being in the space era, where we start as a global community, we start launching spacecraft, right? We start exploring the moon with these spacecraft. So the first one to do this is over here on the left. This is Luna 1. This was a Soviet spacecraft. Its mission was just to go there, measure the pressure and temperature inside of the spacecraft, and then come back. So it didn't do very much. And then we have Lunar Orbiter 1. So this was the first American spacecraft to orbit the moon. Its primary mission was to take images of the surface where maybe we could land things in the future. Luna 9 over here happened in 1968. This was the first spacecraft to land on the moon. It was a very soft landing. It took 9 pictures and then it came back. Very slow progress. No samples yet. No samples yet. So up until this time, even with these orbiters, we are only getting pictures of the near side of the moon. Up until this point, no one has ever seen the far side of the moon, right? It wasn't until Luna 3, right, which is in between the two, right, Luna 1 and Luna 9. Over here on the left, this is the first image that we have of the far side of the moon, right? And before this, we all thought that the far side would be just like the near side, right? That mixture of that light cratered material and that dark flood basalts, right? That volcanic material that comes out. But how wrong we were, right? It's so different, okay? So this is the first image that we have. We had a couple other images with the lunar orbiters. The lunar orbiters are the American spacecraft, right? They didn't get the full far side, but they basically got the limb just on the edge of what you can see, okay? This is Oriental Basin. You can just barely see this, right? You can't see it really well from the near side, but you can just start to see things of this one. So this is along the limb, okay? So before this time, we had no idea what the far side looked like. The lunar orbiter missions were also great because they took some of the most beautiful images, I think, of the Earth, right? This was also our first view back of Earth. This is Earth rising over the limb of the moon. Okay, this gives us that perspective, a little blue dot perspective, looking back at our own planet. Okay, so this is where basically lunar science was before the Apollo missions, before we sent astronauts to the moon to collect samples and do experiments, okay? So to understand how important these moon rocks were to changing our whole perspective of the moon, we need to know, what did we know about the moon before Apollo? And what did we not know about the moon before Apollo? Okay, and how did these rocks help us answer those questions? So what did we know? What did we know about the moon, right, before we sent people there? Okay, what was known? Well, this was our view, right? We had the view of the near side. We just got pictures of the far side. It looked very different, but we knew that there was no water, air, or life on there. We knew that these dark areas, which we call mare, it just means seas in Latin. We knew that these were lava flows, right? Lava that had come up and filled in these craters. We thought that maybe the craters on the moon were from impacts, but it was still debated how many of those craters were from impacts, okay? And we knew that basically because there were all these craters, right, on the surface, it had to be older than Earth's surface. So Earth, even if these were all volcanic, right, volcanoes, they were all ancient volcanoes, there's a ton of them, right? And Earth would have had the same amount, and we don't see them on the surface of the Earth, right? Because Earth has plate tectonics, so we're basically recycling our crust all the time. So we knew that the crust of the moon, this bright area, must be older than the crust of Earth. Okay. So what did we not know? Well, we didn't know a lot, right? Very fundamental things, like how did the moon get there, right? How did it form? How old is the moon, right? What are these bright cratered regions made up of? We didn't know. We still weren't sure about the origin of the craters. And we knew nothing about the geophysics, the interior. Are there moonquakes? Are there earthquakes, right? We had no information about that at all, right? Those are some really big, important questions, right? But luckily for us, in July 16th, 1969, we sent our first crew of astronauts to the moon. So this was the Apollo 11 mission, right? Here's our three fearless astronauts, Neil Armstrong, Buzz Aldrin, and Michael Collins, right? Here they are launching up into space. Here's Buzz Aldrin over here in the lunar module, right? They spent like 4 days in there before getting out on the moon. They also took these really cool pictures. Looking back, you can see Earth, that pale blue dot again, looking over the side of the spacecraft. And after about 4 days, right, they disconnected the lunar module, the landing module, and went down to the surface and took the famous first few steps on the moon. Right, here's Buzz Aldrin descending the ladder. And they spent less than 24 hours. They spent 4 days getting there and less than a day on the surface. Okay? And then they came back. Once we get to successive, missions later on, they spend more time on the surface, but it was a very short mission. They did experiments and they picked up samples. Okay, so where did they go? That's a good question, right? So here's our near side of the moon that we see when we look up in the sky. And there's actually been 6 missions that have sent people to the moon. So here's where Apollo 11 landed over here, but we also have Apollo 12, 14, 15, and 16, 17. So all of these missions put boots on the moon. And when you put boots on the moon, you get rocks back, okay? And they collected a lot, right? Between all of those missions combined, they collected over 842 pounds of material, right? That's a lot of material, okay? You can see, I love these photos, right? So over here on the left, here's one of our astronauts with a handy dandy geologist rock hammer about to chip off a piece of this rock. Here's an astronaut picking up some little rocks on the surface with a scoop, right? And as a geologist, it's really hard because one of our favorite things to do is actually go out in the field and collect samples. But unfortunately for me, I was not alive then, so I couldn't go on the missions with these brave astronauts. But if I did, this is what I imagined it would be looking like. I'd be super excited, and I'd be picking up the biggest big rocks I could find. So this is what it would look like if I could do field work on the moon. Okay, so what kind of samples did they pick up, right? There's a whole range, but the two most important ones are basically soil, right? It's not sand, but it's soil. It's just the loose grains on the surface of the moon, right? This is just what's, think of soil, you just go out and pick up what's outside. But it's very different, right? It's very different than beach sand. You would not want to go to a beach with this sand. And the reason is, over here is a microscopic picture of beach grains, right? Just beach sand. You can see how round they are and smooth. That's why it feels really good when you walk in it. Over here on the left is a picture of a grain from the lunar soil. These are shards, right, of either glass or minerals that have been just broken off of various rocks by impacts. We'll talk about that in a second. Just shards. It's really sticky. It's really difficult material to work with. I work with this stuff. It's very difficult, right? It was actually really challenging for the astronauts too, right? You can see these pictures of the astronauts, they're just covered in it. It sticks to everything and it gets in their eyes, it gets in their lungs, their nose. It's a big irritant. It caused issues with using tools. And this is actually one of the challenges with sending people back to the moon or sending robots or rovers back to the moon, is dealing with the regolith. Like, people are studying this because it's so difficult to deal with. So the other kind of material that they brought back that's important is what we call Breccia samples, okay? So when we think of rocks, right, these are basically the moon rocks, but they're not like rocks when you go out and pick up a rock on the moon, right? They look more like what you would see in cement, right? You see little rocklets in there, and they're kind of all fused together by some other material, okay? And that's kind of what they are, right? That's what they are. And as we'll see in a little bit, this is a product of impact processes, okay? So they pick up all these samples, right? These 842 pounds of samples, they bring them back, and then what happens, right? Well, they come back in these very fancy cases, right? We go into the lab, we break them open. This is Edgar Mitchell from Apollo 14. He's showing off some of the rocks that was collected on the surface, okay? And then, you know, we curate them, right? Like a curator at a museum, we curate the samples, okay? And this is at that, if you remember the picture of me at the NASA Space Center with the moon rocks, this is the same laboratory. So we have the laboratory where we cut them off, we categorize them, catalog them, do a little preliminary characterization, and then we can send them off to laboratories, right? All kinds of laboratories all over the world. This is just me showing an example of, these are the 5 different laboratories that I've used to study the moon rocks, okay? We can send them all over the world. We can measure all different kinds of things. And I'll tell you why in a little bit, why it's so important to bring them back to Earth. Okay. All right, so I told you that I was going to show you why having the samples here is so important, okay? Why did getting these samples revolutionize what we think of the moon and how we think of our solar system, okay? So let's go back to that slide where we talked about the pre-Apollo knowledge. Before we went to the moon, what did we not know, okay? We didn't know how the moon formed. We didn't know what the crust was made of. We didn't know how old the moon was. We didn't know anything about the inside. And we also didn't know where the craters were coming from. So I could talk hours and hours and hours and hours about every single one of these, but I'm just going to choose 2 and show you, just for these 2 examples, how we're able to answer these questions with the moon rocks, okay? And the 2 questions I want to focus on are, how old is the moon, right? A very fundamental question. And then the origin of craters, where do they come from? Because I'm a crater person, I love craters. So let's talk about this first one, right? How old is the moon, okay? Before Apollo, we had 2 estimates, 2. One was that the moon was 100 million years old. The second was the moon was 3.6 billion years old. These are very different ages. The moon is very young or the moon is really, 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 really old. Okay, this was our best guess, which in all honesty is not really a guess when you have that far of a difference, right? You can't really do much with that. Okay, so how do we do it, right? And the way that we do it is we actually date how old these crustal rocks are, right? How old is this highlands, this light material, the very cratered old stuff? How old is it, okay? So the way that we do that, and you might have heard of, you know, radioactive decay, okay? You might have heard of like carbon dating, okay? Carbon dating, it's a very similar concept, except carbon you use for much younger things, and you also use for organic things, right? So carbon, you date really, really young things. I'm just showing you an example. So the way that this kind of radioactive dating works is you have a radioactive element, like over here on the left. I'm showing you an example of uranium, right? Uranium is obviously radioactive. 238 uranium, this is our isotope. So we have some uranium, it's radioactive. It will undergo radioactive decay and produce something else, okay? This produces lead. In this system, we call uranium our parent and we call lead our daughter. It undergoes different decay, emits a bunch of stuff, turns into lead, okay? We do the dating by, we measure how much parent there is, we measure how much daughter there is in the sample, and we know how quickly one converts into the other, and we can figure out how old the sample is. This is very similar to if I knew you were driving in a car and I knew how fast you were going and I knew how far you've driven, I could tell you how long it took you to get there, right? Same concept. If I know how quickly uranium is going to lead, and I know how much of the parent the daughter is, I can tell you how long it's been decaying. So that's how we get the age, okay? By this kind of radioactive dating. And there's many, many, many systems that we can use, right? There's many different radioactive parents, right? This is the uranium lead system I just showed you. There's all these different kinds of systems. And they're all very good at dating things that have various ages or different kinds of rocks, right? It just depends. You choose the system that's best for dating what you want to, okay? And in this case, we want to know how old the moon is, right? So what do we choose? How do we choose? How do you choose a geologic event that is the formation of the moon? Okay, that's kind of it's a hard concept to think about, but the way we do this is we basically date when the core of the moon forms, okay? We know, like Earth, right, we've got a core and a mantle and a crust. The moon also has a core and a mantle and a crust. So basically, from a geologic perspective, we're saying that the moon forms when its core forms, okay? It's considered a complete body when the core is isolated, okay? And the system that we use, right, is hafnium tungsten. Hafnium decays to tungsten. And the reason that we do this is that, tungsten really likes metal, hafnium doesn't. So when the core forms, you get some chemistry that happens because one wants to go with the metal to the core, the other one doesn't. It's a really good marker of when you have that metal separate. Okay, so what was our answer, right? Our answer is the moon is 4.56 billion years old, much older than either of the estimates that we had prior to going out to Apollo. And the interesting thing is that the moon's core formed at the same exact time, okay? So both the Earth and the moon formed 4.56 billion years ago, okay? It's also a clue that we use to understand how the moon formed, but we can talk about that later. Okay, so we now have, because we have these samples, because we can measure them in our lab, we can get an age of the moon. And often when I give talks like this is the point where someone says, well, why can't you do that on a rover, right? We have rovers that are on Mars that are going around and taking various measurements. Why can we not make this measurement on the moon? Well, here's a very simple comparison that will highlight this, okay? So this is on the left, our Mars 2020 rover. This is a rover that most recent rover, and it's up there caching samples right now. This rover weighs about a ton, okay, 1.2. Over here on the right, this is one of the laboratories where we make these kinds of measurements, okay? Do you see this red thing right here? That is the magnet, just the magnet. The magnet for this instrument weighs 1 to 2 tons. So this, just one component of this instrument, weighs more than anything that we have put on another, more than this any rover we've put on another body, okay? So downsizing, miniaturizing this kind of laboratory and putting on a rover is very difficult. So this is why when people talk about getting samples back and the importance of getting samples back is that we can't do a lot of the stuff that we need to do to answer these important questions without having in these very complicated laboratories with instruments that weigh a lot, okay? Okay, so we've talked about the age of the moon, right? We've got 4.56 billion years old, same age as the Earth. So the other question that I was going to show why it was so important going to the moon is the source of the lunar craters, right? So before Apollo, we kind of thought, quite a few of them were from impacts, but we weren't sure if they were all impact or volcanic and that kind of stuff. So it was still highly debated, okay? So sources, lunar craters. So what did we learn by going to the moon, okay? Well, the first big picture observation is as we got closer and closer to the moon, right? The astronauts are in their spaceship, right? They're going closer and closer and closer. They get in the lunar module, they start going down, they get closer and closer and closer. And we start seeing craters that's smaller and smaller and smaller and smaller sizes, okay? Craters on the moon range in huge size, okay? This is Oriental. That was that image, the crater that we saw earlier in one of the orbital images, right? This is a huge multi-ring basin, right? Almost 1,000 kilometers, huge craters. So we get closer, we get smaller craters, we get smaller ones, 28 kilometers, we get a kilometer, all the way down to microscopic craters on grains. You can see impact craters on individual grains within the lunar soil, okay? Volcanoes don't produce craters that are that size, okay? The only geologic process that can create craters across this whole size range is impacts, because you can have impacts across that whole size range, okay? So that's our first clue, that maybe they're all, or majority of them, are from impacts. Another clue came from the fact that if we're looking over here at this rock sample, right? We talked about breccias, they kind of like cement, like little pieces of rock that have been fused together with cement. This is all done by the impact process. Impacts have been hitting the surface, or impactors have been hitting the surface of the moon, making craters and processing the material over the entire history of the moon. They break things up, they fuse it together, they break stuff up again, they fuse it together, they break it up, they fuse it. And then this regolith, right, this soil, we saw those like shard-like grains. Those are just basically the surface of the moon being pulverized, right? Just constantly impacted by things of all kinds of sizes, and it's just pulverized, okay? So even the samples that we get back are just completely different than what we see here on Earth, okay? And the last clue that made us come to the conclusion that the impacts are the source of all the craters is we also saw what we call high pressure mineral phases. So these are basically minerals in the rocks, or areas within minerals of the rock, that can only form at very, very high pressures, or the result of very high pressure events, okay? And so we see that, right? So these are just microscopic images. This right here is what we call mescalinite. This is basically a pyroxene, which is a type of mineral that has been shocked by an impact event and turned into a glass, right? You've basically broken up the entire crystal structure of this mineral and turned it into a glass, okay? That only happens in impact events where you have very high shock waves, very big big energetic high pressure events, right? And all of these grains, they're just shards. So putting those all together, right, basically came to the conclusion that craters come in all sizes, from giant, 1,000-kilometer basins down to microscopic craters. All of the material we got back looks like it's been pulverized or, just recycled through multiple impacts. And then we see all these high pressure phases in these samples. So basically, after we saw all of those, we came to the conclusion that yes, the source of the craters on the moon are all impacts. Okay. So those are just two of the questions that we were able to answer, but that list of questions that I showed you of the unknowns, we were able to answer many, many details about all of those. But there's still lots of unknowns, right? There's still a lot we don't know. And actually, lunar sample research, like research that's being done on these Apollo rocks, is still going on today. So I sit on an advisory board for NASA where we review proposals by scientists to study these samples. And we have to meet many times a year because there's so many proposals. So there's still a lot of research that's being done on these samples, okay? Because there's still so much more that we can learn. And this makes me really excited for two reasons, right? There's still a lot of research going on. But if we think about just the fact that we went to the moon and we brought back 842 pounds of material, we were able to do all of this science, okay? We were able to answer all of these very fundamental questions. That's really exciting because as we look forward into the next decade or so, or even just the next 5 years, right? NASA is calling the 2020s as the decade of sample return. We are going to get a bunch of samples back. We've already got a bunch of samples back, right? The Chinese have already landed on the surface of the moon and brought samples back. The Japanese have gone to an asteroid, right, with Hayabusa 2 and brought samples back. OSIRIS-REx has collected samples and will be returning. We are going to be putting rovers on the surface, right? We're going to be putting people on the moon to bring back samples. And up here in the right corner, right, we have Mars 2020 on the surface collecting samples, and we've already started planning the mission that's going to get them. We are going to get so many samples back in the next decade. And if these samples can help us answer questions like the Apollo samples have done, we are going to learn so much more about not just the moon and Mars, but everything that we learn about the moon and Mars helps us understand Earth, right? Earth as a body within the solar system. So I think that this is a really exciting time to be around, and this is a very exciting time to get into studying materials like planetary materials, because we're just gonna have decades and decades more of really fun research. So with that, I will leave you with my favorite picture I like to start with. I will also end with the picture of the near and the far side of the moon. I hope you had a great time going through this journey of lunar exploration with me. I hope you are also equally as excited as I am about moon rocks. I am always here at the University of Colorado you can always send me questions, and I am happy to answer them or find times to chat. So I hope you all enjoyed the talk, and I hope you enjoyed the rest of your week. Thank you for coming.